인사할 시간도 없습니다.
안될과학 인터뷰입니다.
So, before we begin, just want to open the floor, quick intros. Charina, she currently leads as the Chief Operating Officer at Google 컴퓨터'의, and she oversees the business strategy, the operations, partnerships, and public engagement.
I'm very honored to interview with you this time.
Yeah, thanks so much, Hang-sung. And I'll just say I'm also honored to get to meet you.
Okay, so let me begin with the first question. Could you please tell us about the Google Quantum AI Lab and what you do there?
Yes, absolutely. So maybe actually, Hang-sung, I'll pose a question to you and your viewers also. Imagine that you have a very tall closet with a million drawers and you hide a sock in one of the drawers. On average, how long would it take somebody to find that sock? How many drawers would they need to open on average?
Oh, let me see. There's no average. It will take forever. I want to say that. There's no average time. How can even say that?
I know, actually, and it's funny for me. I feel like at home, it's always the last drawer. So for me,
Right.
999,999. On average, actually, with classical algorithms, it takes about n over 2. Imagine a distribution. So on average, it would take about 1 million over 2 in this example. You'd have to open about 500,000 drawers to find the sock. However, with quantum algorithms, you actually only need to open the square root of n. So square root of 1 million drawers, 1,000 drawers, and you would be able to, on average, find the hidden sock after 1,000 drawers.
Wow.
Yeah, so that's just an illustration of why quantum computing is so important, right? It's exciting because for some certain types of problems, you can imagine, and actually there's theory that demonstrates you should be able to access solutions much faster, potentially more accurately, potentially more cheaply, or some combination. And so for Google, it's very important for us, we're a computing company at heart, amazing things being done with classical computers, right? And we'll always use them. But to access these other classes of problems, we think it's very important to invest in quantum computing as well. That's the Quantum AI Lab at Google. Our mission is to build a useful quantum computer, and we are very focused on that goal.
All right, that's very cool. That's very exciting. And I totally agree that Google is leading all the current computing skills and technologies and everything. And I'm very impressed that you are also leading about the quantum computers as well. So you're working in the Google Quantum AI. Everybody knows what the AI is, but what is the distinction between that AI and the quantum AI being developed at Google?
Yeah, it's a really good question. So today's AI, right? And I think we've seen it explode also in the last
everywhere.
Everybody is talking about it. It's in all the newspapers, on all the billboards. Today's AI, and it is amazing, right? The computing has gotten so much more powerful even in the last 1, 5, 10, 50 years. There's been a lot of advancements. However, today's AI, artificial intelligence, right? It is still run on classical computers, right? Computers that operate according to classical mechanics, utilizing bits, right? Bits that are state of 0 or 1. And again, it's amazing to see the developments. I think we'll continue to see, a lot more in that space. However, we know actually that even with the best classical computers, there are many problems that will be impossible to solve. So just to give one example, right now with classical computers, we can approximate, for example, how electrons are moving through material, or how electrons are interacting with light, with photons, right? And these types of processes are super important, right? They dictate things like, our proteins, how pharmaceuticals interact with in our bodies, the design of new solar cells, like how light and electrons move through material to harness electricity, batteries, all sorts of materials in the world. And right now, with the best classical computers, even if you use supercomputers, you can only approximate how those types of behaviors are occurring in the materials. The belief, the theory, and the hope for quantum computers is that quantum computers operate according to quantum mechanics, right? And that is the exact same type of physics that happens in our proteins, in molecules, in solid state materials, and others. If you have quantum computers that can actually operate according to quantum mechanics, the idea is that they can simulate exactly how those quantum processes are occurring, and that you would actually be able to find exact solutions or much more accurate solutions much more quickly than would ever be possible, even with the best classical AI.
Wow. So best classical AI can only approximate the very complex or complicated problems, but the quantum computers, quantum AI computers can find the exact solutions or exactly mimic what the proteins or what the materials happening inside of the materials, right? That's what you meant
Exactly.
about.
That's the hope. Nobody has demonstrated it
Right.
experimentally yet, but that's why we try. And ultimately, I think we really believe that classical computers, classical AI, and quantum computers, quantum AI, will be complementary, right? You're
Right.
still going to need classical computers for many types of problems, but the addition of powerful quantum computers will help access these classes of problems that are currently not possible.
So next one is, can you briefly explain about the quantum computers being developed by the Google Quantum AI? I mean, is it correct to base the primary concept on the quantum entanglement? Is that right?
Yes, it absolutely is. So there's a couple things that are needed for quantum computers, right? The first is you think, for those of your viewers watching that remember, I don't know, high school or college chemistry or physics, thinking back to quantum systems, right? That means that you have discrete energy states or discrete levels, right? And so one of the things that is necessary for a quantum computer is to have quantum system that can access, two specific levels. In chemistry, you might think of it as the ground state and the excited state.
States.
And so being able to be in, either the ground state, the excited state, or some, superposition across those two. One element that is additionally very important in quantum computing is entanglement, exactly as you said. So the idea of being able to not just have, one quantum system in a superposition of states, but to have multiple of those working in concert together, right? If you imagine, let's say, one quantum bit, one qubit, right? And I know maybe later we'll talk about the different materials and different ways that you can create that. But imagine you have one quantum bit, you can access some superposition of ground and excited, or 0 and 1, how you want to label them. If you have two quantum bits that are now entangled, right? Entanglement is correlated together. Their behavior is correlated in some way. You can now access not just a superposition of 0 and 1, but two superpositions of 0 and 1 acting in concert. And now imagine that you can get 3 or 4 or 5 or all the way to n quantum systems entangled. You can actually start to access an exponential number of states, which gives you significant computing power.
Right. Okay. Oh, that is very impressive. I only thought about the quantum entanglement happened like only 2 or 3, but you can expand as much as you want or you can, right?
Oh yeah. So I guess you can is generous. So far, I think we've demonstrated up to on the order of 10 to the 2, on the order of 100 or so qubits. That's kind of where the best in the world is right now, which is really quite awesome. But theoretically, you can
theoretically
millions, and that's what we're going to try to get to.
So qubit is the same concept of in the classical as a bit, right?
Yes, exactly. So for as you said, bit, right? It's short for binary digits.
Right.
So that's what people use for classical computing, a 0 or a 1, right? Binary can be in one of those states. Quantum bit, I guess you can think of it as the quantum analogy of a bit, right? So qubit is that analogy where you can now be in the ground state or the excited state or 0 or 1 state, but differently from classical computing. With quantum mechanics, right, you can also be in that superposition, right? So some linear combination of those two states, you can expect a distribution across those, and that is uniquely quantum phenomenon that enables you to access some different compositions of states.
Great, thank you. So next one is, if perfected to the stage of the commercialization, quantum computers are considered to be a far cry from today's supercomputers. However, the development process is believed to be difficult. So what are some of the difficulties in constructing a quantum computers?
Yeah, there's a lot of difficulties.
I know.
And I'll just emphasize, we talked about this a little bit before and you mentioned it in your question, but again, quantum computers, we believe, will be a far cry from world's best supercomputers on certain types of problems. They will not be amazing and better than classical computers on every single type of problem, but for those certain types of problems, again, is why we're pursuing quantum computing in the first place. I think one element to think about, maybe we think about it in terms of quality of the quantum bits as well as quantity. So quantity is easy for many people to think about, right? They think about, okay, the more quantum bits that you have, right, the more you can entangle together,
Right.
the more computation you can do. And that's certainly true. Right now, as I said, we and others, right, there's a lot of really great players in this space, a lot of people working on the problem, which is really good. Right now, the best is on the order of about 10 to the 2 qubits. So about 100 or so, 100 qubits. What is expected and needed for quantum computing is actually not 100 qubits, 100 physical qubits. It's expected that we'll need at least 1 million or more physical qubits.
Million.
At least, to really start to access some of these tough problems like we were talking about in material science and chemistry, things like that. So that is an order of magnitude of at least 4, at least 4, from going from 10 to the 2 to 10 to the 6,
Right.
to increase the physical qubits. And that comes with a lot. How do you think about the scale up? How do you get not just 100 qubits on one chip, right? How do you get 1 million? Do you need to link all the chips together? Again, we'll talk about all of the challenges there, but scale up is certainly one. The other I really want to emphasize, because people talk a lot about quantity, but maybe not as recognized or discussed, is the idea of quality. You could have the most qubits in the world, but if they're horrible, you won't get any computation
Right.
out of them.
That's true.
So the quality also really matters. And one measure of quality that you can think about is the qubit error rate, the logical qubit error rate. So today, again, just to give you a sense of where we are right now, the best quantum computers, right, our early prototypes, they have an error rate of about 1 error in every 100 algorithmic steps.
100? Just 100?
Yes, just 100. So, and that's already been quite a lot of work to get to this stage, to make 1 error in every 100 algorithmic steps. But it is expected, again, if you look at some of these, ultimately exciting, inspiring problems like in chemistry and material science, it's expected you will need at least 1 million or more algorithmic steps. And so what we're trying to get to is from 1 in 100, an error rate of 1 in 100 algorithmic steps, to an error of 1 in 1 million or more algorithmic steps. So again, that's from where we are now to where we need to be. That's another 4 orders of magnitude in quality, maybe even more. And we could talk about specifics, but there's a lot of things we need to do to try to improve both the quality of our qubits and then scale them up.
So quality and quantity, actually, those two are everything for the quantum computers, and actually not only computers, but everything else. So you're pursuing the increasing of the quantity and quality. So you mentioned about the error range.
Yes.
Just mentioned about it. So with that, Google announced in February 2023 that you achieved an experimentally significant outcome for quantum error corrections. So it was the world's first successful demonstration, and it was published in Nature. But what exactly is a quantum error correction? I think you just mentioned about a little bit about, but I hope you can explain a little bit about the easier way to what the quantum error correction is, and what is the consequence of what you achieved actually.
Yep, definitely. So, in our last question, we were talking a bit about the need to have very few errors for a number of algorithmic steps. I think everybody can understand that, right? You want to run a super large problem. To get an accurate answer, you need to have as few errors as possible. However, when you look at how quantum computers are currently built, right? And they're built out of actual physical systems, right? They're hardware. There's always errors that come associated with it.
Mhm.
In fact, that's true with classical computers too. If you've got bits, the bits are not always perfect. Sometimes there's errors due to the hardware or due to the environment, cosmic rays, or other things. And so our classical computers also need error correction in order to really make sure you've got the right computation coming out on the other end. With quantum computers, each qubit, each quantum bit has error introduced from a lot of different places, right? Sometimes you just have noise. Sometimes you
Right.
have interaction with the environment. Sometimes, we made a measurement error. We actually incorrectly understood what happened. We also have to control the qubits. And so maybe sometimes there's an error in the control electronics. So there's a lot of sources of error. With a quantum computer, where you want to get to it, again, is to run useful, important, large algorithms on a quantum computer. However, if you have one quantum bit and it has some error, then you add another quantum bit and another quantum, they all add error. And up until this point of our Nature paper in February of this year, every time that you would add more qubits, what people noticed is you actually added more error. So
Right.
unfortunately, if you need to scale up to answer some really tough problems, but then you're also increasing your error, you won't be able to get to the quality that's needed.
Right.
Solve those problems. So our paper was actually really exciting. I think, again, it's very early stages. As I said, we have a long way to go, but this paper was a milestone for us and for the community in demonstrating, for the first time, you could add more qubits and demonstrate that instead of increasing the number of errors, we were able to add more qubits and protect against errors. So we went
Oh,
from a 3x3 grid to a 5x5 grid and actually saw that the error came down a little bit. So we showed
wow.
there was a theory of quantum error correction. Look, if you can add more, you're kind of providing some redundancy, I guess is a way to think about it. You're protecting for the errors, and maybe you could, accommodate some of the errors and start to mitigate that error out there. What we showed for the first time was as we went to a larger grid, we were able to actually correct the error and go to lower error than we had with the 3x3 grid, which kind of is a moment to say, hey, maybe this is possible. Maybe we can go beyond 5x5. Maybe we can go to 7x7 or 11x11 or even bigger out to, million physical qubits and actually lower the error, which is what we need for actual useful quantum computation.
That is very impressive. Actually, that is, I mean, if it really works in that way, that's very impressive. So you just mentioned about the milestones. So Google has established about, I think, 6 milestones, right? A
Yes.
significant milestones in Google back in 2019. I think that was the first milestone. Following the quantum processor Foxtail and BriskCon, you announced that you had reached quantum supremacy with the third generation processor Sycamore. So, what is a quantum supremacy and what was the achievement at that time?
Yeah, exactly. So quantum supremacy, another term that people also use is beyond classical.
Beyond
Essentially,
classical.
the first demonstration that a quantum computer can perform a task that is impossible, intractable, would take way too long on a classical computer.
I have a key question. Do you say that when you say the classical computers, that is the classical supercomputers? What's that mean?
Yes, that's a really good question. So classical, in this case, quantum supremacy or beyond classical means beyond the best classical supercomputers.
Okay.
That would take the world's best supercomputers very long time to ever achieve. And long time in this case was 10,000 years. So we could simulate, it would take the
Wow.
world's best supercomputer 10,000 years. On our Sycamore chip, we were able to perform the task in 200 seconds.
200 seconds. Really? Wow, that's very impressive. So the Sycamore was a third generation. I believe that you probably developing fourth generation processor to make a progress on quantum error correction on its own.
Yeah. So a couple of things. One, to note, as you talked about the 2019 experiment, it was very exciting. For us, it was as you said, our first milestone. It was a breakthrough in demonstrating, hey, people thought quantum computers can do tasks. This is an experimental demonstration that we can perform a task that would take classical supercomputer, 10,000 years. On quantum computer on Sycamore, we can actually take about 200 seconds. A couple of things to note though. First of all, that was a benchmark experiment, right? So it was for people following that, it was you could think of it as a proof of principle. It was on an experiment called random circuit sampling, a task that is basically sampling, random quantum circuits and trying to output probability distributions. That's great, but one of the things people are trying to do is also look at okay, what other really useful problems are we going to be able to solve? So we could talk about that in a bit. I would call that maybe a benchmark example, but we're still continuing to look for and develop quantum processors that can solve really useful types of problems like the ones in material science and chemistry we talked about earlier. A second point that's really important for people to understand is you never have computing at a standstill, right? Like we're, as you said, trying to pursue fourth, fifth, all the next generations of the quantum processor. Classical computing also continues to get better and better and better and better and better, right? So this task that used to take the best classical supercomputer in 2019 on the order of 10,000 years, that was estimated. Now that can be brought down to seconds in today's 2023 best classical supercomputers. In fact, actually, our quantum computers have been getting much better as well, but you can imagine it's actually, as some people call it, a race or kind of a cat and mouse game, but actually it's really exciting for the field of computing as a whole, right? You improve quantum computers, that inspires people to improve classical computers, and all of them continue to get better. So that's what we're pursuing.
But 10,000 years to the few seconds, that's very impressive. Oh, wow. That was amazing.
Yes, and a huge shout out to those classical computing experts who really pushed the boundaries on new classical algorithms, better hardware. All of that is really quite a testament to that field also.
So next one is I saw your couple of your previous interviews, and you've stated that the quantum computers will need to be millions of cubic feet in order to be feasible. That's why you just mentioned about it. Is this the point at which we will reach the sixth milestone? And what impact do you anticipate having on the world at the time if you achieve the sixth milestone?
Yeah, exactly. So you talked about and alluded to our Google Quantum AI roadmap. We've got six milestones. Milestone 1 was the one we just talked about, quantum supremacy beyond classical. Milestone 6 is this idea of actually getting to 1 million physical qubits, as we talked about. In quality, we also think, quantity, 1 million physical qubits. Quality, we need at least, 10 to the minus 6, one error in every 1 million algorithmic steps, hopefully even better by then. Yes, that is our end goal. As I said, our mission is a useful quantum computer. We think that milestone 6 is kind of the marker for what would be very useful. When we talk about useful, what does useful mean? It is actually intended to represent a quantum computer that can solve some of these very difficult problems, as I said, that are not possible on today's classical computers. So we do believe, and a lot of the theory supports this assessment, that we are going to need probably on the order of 1 million physical qubits or more to start solving some of these tough problems in material science and chemistry and others. We also are going to need, again, that quality, the one error rate in every 1 million or more algorithmic steps, because these types of algorithms to solve electronic structure for materials or things like that are very large. And so we don't want to have too many errors. And so where we are headed is to try to get there. When you talk about the impact on the world, again, you could imagine if this tool existed, it could help in a lot of different sectors, right? It could help for sure in the pharmaceutical sector, in the energy sector, designing new batteries, designing new solar cells, thinking about all these elements of sustainability. Could absolutely help in the chemical sector. So could we help to use a quantum computer to design better catalysts for fertilizer or for important reactions? It might help in a number of other ways. So far, I've also largely focused on chemistry and materials. For me, it's kind of a holy grail. I think that's one of the most exciting opportunities, but there's a lot of work that shows, hey, quantum computers may also be very helpful in tasks like machine learning, in tasks like potentially optimization and others. And so there's lots of other fields, including simulation, that this ultimate milestone 6, this ultimate useful computer could play a role in helping to address and actually solve many of those types of algorithms.
Okay, seems like you have a background about the chemistry. That's how I felt. And
You
in
do.
my, oh, really? You
I
do?
do, yes. My PhD is in physical chemistry,
Oh,
so
that's
I think that's
yeah,
why
that's how I felt. And this is very curious questions that how much is the cost about the quantum computers if it is developed like the everyone has a for the classical computers everyone has their desktop or laptop they have, but is it possible to have each private family has the quantum computers for later on? Do you think that will happen?
Yeah, it's an interesting question, and imagine if we went back 50 years and
Right.
people were asking the same questions about the classical computers. Honestly, I don't know if anyone would have predicted, like, look, you have these phones, they'd be super powerful. The first classical computers were gigantic, right? These
Right.
took up entire rooms, needed a lot of cooling systems, and they were incredible investments at the beginning. And now we've seen the price, Moore's law, better chips, all of these things come down and down and down so that everybody has multiple computers in their home. Really, for many people, I think with quantum computers, it's a very interesting question. Certainly right now there's a lot of investment that needs to go to even the research and development, right? Like, we don't even know how to build that ultimate quantum computer. We have some ideas. We have a roadmap, as I said, we're at about 100 qubits and about 1 in 100 error rate, but we think it would be an amazing tool for humanity. But if we do, I would assume that, better engineering, better scaling, all these things, just as with classical computers, the cost can come down. Maybe at the beginning, it's, initial customers or initial users that try it out on major big projects, like you said, maybe for astronomy, maybe for material science or other big things. And then as the costs come down and the quality goes up and all these things, maybe becomes more and more accessible.
How long will it take probably like if possibly all family has the quantum computers?
Yeah, it's fun to think about the
Yeah.
future. You know this, you're a scientist yourself, science, you can never predict exactly
Right. I agree.
or
I totally agree there.
or the outcome. But in our best estimation, and we do have a roadmap and very specific steps that we know are needed and requirements towards our next milestone 3, which is actually we didn't talk about it yet, but milestone 3 is to go from on the order of 100 qubits to 1,000 qubits. So we want to go up about 1 order of magnitude. And then we want to go from about 1 error in every 100 algorithmic steps to 1 error in every million, what we know is going to be useful. So we want to go about 4 orders of magnitude in quality. That's going to be very difficult. We have a technical roadmap to get there. We think that's going to take, maybe we can try as early as 2025 to demonstrate that. Maybe
2025.
Maybe, we're ambitious, but it may be 2026 and maybe 2027. You never know how these things are going to go, but we have a technical roadmap to get there. To get all the way to milestone 6, the 1 million physical qubits, 1 in a million or better error rate per logical qubit, we estimate that will probably take on the order of maybe 10 years. So
10
right now
years.
we're in 2023, so maybe about 2033 to get to this milestone 6 computer.
Oh, that's fun to like imagine. So, we're in your opinion as an industry leader, because you're one of the leader in the Google quantum AI. When do you believe quantum computers will become the mainstream of the computing? Because now mainstream of the computing is actually leading by the classical. Because you said that your milestone will be 60 milestone will be in 10 years. So it will take more than that. So any thoughts about that?
I'm not sure that quantum computers will ever become the mainstream over classical computers. We talked about this a little bit earlier, but classical computers will always be really important, I think, for many different tasks. And I think you always want to use the simplest potential solution, right? So for lots of different tasks that we use classical computers for now, even basic addition or subtraction or things like that, I think we'll always want to use classical computers for those types of problems. However, again, quantum computers ideally are going to help us access certain other classes of problems. And if we can get to this milestone 6 or other, ultimate useful computer, I do think ultimately we'll have classical and quantum together as kind of working in concert, right? So I think that will ultimately be the case. In terms of when a quantum computer would be accessible to the general public, it's an interesting question. One thing I'll tell you, and actually all of your viewers, is that at Google we designed a program, a machine called Quantum Virtual Machine. QVM. So actually, it's completely accessible. It's open source. Anybody can try it. So what we did was actually built a virtual machine trained on and built on our actual hardware, so that people can play around with our Sycamore processor, virtual version of our Sycamore processor, try to figure out different quantum gates, apply and try to build an algorithm and actually apply it and get some answers out. So I would say that's accessible to everybody. Absolutely try it out. And I think, look, there's going to be continued progress, right? Even as we and others, lots of others in the space, are all importantly working toward, fault tolerant, giant quantum computers that can solve real problems. It is very important for others in the outside, right, in the public, to actually start accessing these types of computers as well and start to see how do they work, or can we use them better. Even before we get to that ultimate quantum computer, we believe that if you have not 1 million qubits, but maybe 10,000 or 100,000, you can start to access some simpler types of problems that maybe you're able to outperform classical computers. At those times also, and even now, we partner with academia. We actually do provide some specialized access to our computers. I think that will just continue even before that ultimate milestone 6 computer. We do want, and we will have many opportunities for people to continue to access, try out new problems. The ultimate goal, right, is so many problems in the world. At Google, we're only thinking about some very small fraction. If you're able to open it up, people can actually solve all different types of problems that may be useful for them.
That's very impressive. So actually using a virtual machine, you can actually access to the Sycamore right now.
Yeah, so try it out.
I will try it tomorrow. So the last one is actually many people are interested in the quantum computers because they are supposed to complete the fourth industrial revolution right at this time. And I don't want to conclude by asking our subscribers who watching this interview right now, who appreciates science as a culture through our channel, YouTube channel, Unreal Science, and are keen on quantum computers. Any comments you'd like to share with our viewers?
Yeah, a last comment that I will share, again, since your viewers are science enthusiasts, scientists, people that love science, again, myself included there, I would say, many of us are excited about science because it's super interesting. You learn more about how the world works. You learn more about how we as humans work. And you look around at nature, right? It's gorgeous. It's beautiful. You take a walk, you see the blue sky, green leaves, beautiful flowers. In fact, all of that nature operates, according to quantum mechanics. Quantum mechanics is the reason why the sky is blue, or why you have a beautiful rainbow or color in a flower.
I have phone as well.
Exactly. And I would say, with this pursuit of quantum mechanics and quantum computing, we are actually trying to do exactly that, harness nature, what nature already does, how it's incredible, how it already performs, to perform some other new task of computing. So we are trying to harness nature to do something else that we find is useful. And there's a lot more to learn. So we're excited about the journey.
Oh, that's very great. I really, and on behalf of the viewers of the Unreal Science, we are very appreciate your insights and comments for this interview.
It was really fun talking with you, Hong-Sung. So thank you for taking the time also. 감사합니다.
Thank you so much.
인사할 시간도 없습니다.
없습니다. 안될과학 인터뷰였습니다. 감사합니다.